MRL calibration tape, IEC equalization, at 355 nanowebers per meter, fringing compensated. Roll the intro.
Let's talk about what we actually calibrated on this 80-8 and why. This machine originally left the factory set up for 185 nanowebers per meter. For how we're running it now, we're bringing that operating level up to 320. But doing that the right way means recalibrating the entire signal path, not just turning things up and hoping for the best. It's kind of the way we found the deck. So here's what we will be working through. First, I set the E to E calibration, electronics to electronics, confirming the known input level, minus 10 dB, actually registers 0 correctly on the VU meters, and then minus 10B at the outputs, before tape ever enters the equation. From there, we calibrate playback levels on both the playback head and the record head. So repro and sync, playback, actually agree with each other. Then we move to erase current and record bias, including where to probe on the RP boards so measuring the right thing isn't guesswork. And finally, we set record levels and record bias, aligning the machine so that 0 VU really means 0 VU on 320 nanoweber tape, not just on paper. You'll notice we'll be going back and forth from 1K test tone to 10K test tone and back to 1K. Again, this is the messy side of analog, but it's very important and you're going to get to see why. So sit back, relax, and enjoy the sultry tones of
1 kilohertz.
Over and over and over again. While I'm waiting for the pinch roller to arrive, I'm going to go ahead and do the calibration of the electronics. The service manual does not actually walk you through doing an E to E alignment. It doesn't mention doing any kind of a calibration on that. I'm going to assume that the manufacturer, Teac, kind of felt like, okay, well, we're going to go ahead and set that at the factory, and then you're kind of authorized, allowed to changes to the playback levels and the record levels and the bias, because the variable in all of this, as far as the owner is concerned, you're going to be using different tape. When this deck was manufactured, they were using 250 nanowebers per meter tape, 250. We'll just call it 250, okay? And interestingly enough, the service manual indicates that it was calibrated at 185 nanowebers. Yet you're expected to use a 250 nanowebers alignment tape. But here's the rub. I can't get my hands on a 320 alignment tape. All I could get my hands on was a 355. So with 250 nanowebers being the reference, and the fact that we're going to be using 320 tape for the sessions, and we're going to align the deck using a 355 tape, a couple of things have to be taken into consideration, all right? So at 250 nanowebers, 355 is going to be on the order of about plus 3.5 dB, thereabouts. And 320 tape is actually going to be about plus 1 dB over 250. So if I were to calibrate the deck at 250, then the 320 tape that we use is going to be plus 1 dB. And the alignment tape is going to be plus 3. So I have to basically fudge everything back to the median being 320. 320 will become our 0 dB reference. And that's with a minus 10 dB input. Now, a lot of numbers I just tossed at you, and I apologize for that. But these are things that have to be taken into consideration with what I'm about to attempt. The first thing I want to do is go ahead and check the calibration of the actual E to E. Now I'm going to be feeding the deck a minus 10 dB 1 kilohertz tone. 0 dB on the VU meter at 0 is expected to be minus 10 dB on the input. You feed it a minus 10 dB signal, the VU meter is going to read 0. dB is not really a voltage reference. The purpose of dB is to be able to determine if something is lower than normal, 0 dB, or above 0 dB, according to the service manual, and they are correct, is actually 0.3 volts. What the service manual doesn't tell you is that's an RMS value. So 0 at minus 10 dB is going to be 0.3 volts RMS. And the scope is going to be measuring peak to peak voltage. And when you convert minus 10 dB, which is 0.3 volts RMS, is going to be 0.88 volts peak to peak. My digital multimeter is registering 0.315 volts. That's RMS at 1 kilohertz. That was a lot of information, so I'm going to pause there so that people have an opportunity to skip over it. Now, with minus 10 dB at 1 kilohertz going into the meter and the scope, I now know that my tone generator is set correctly. We're going to call it that anyway. All right. What I'm going to do right now, though, is I'm going to undo the bypass on the deck, and now I'm feeding tone through the deck. The meter has changed 1/1000th of a volt, okay? 0.316 volts RMS. The scope is reading 0.88 volts peak to peak. What is the VU meter reading? Dead on at 0 dB. What I want to do, though, is I want to show you how to make those kinds of adjustments. These adjustments that you're seeing here, okay, these are all for the playback and the play EQ and record level and record EQ and bias and all that kind of stuff. But the VU meter and the overload meter are way back in there. So I'm going to have to actually extend the circuit board. So there we have it. 0 dB VU, and the output is still 0.88 volts peak to peak and 0.316 volts RMS. Now, moving on, let's go ahead and check the overload meter. Now, the way Teac has set this up is that the overload meter, which will respond to transients at 10 dB over reference, which if we're using a minus 10 dB input, then that just means minus 10 plus 10 is 0. So at 0 dB input, the meter is going to slam. It's going to just be right off the scale. And the overload light should come on. You really want it to just be coming on at 0, which is plus 10 over reference. So I'm going to go ahead and change my tone generator to 0. And the overload light should come on. And there it is. Now, the thing is, what if it came on at a lower level? All right, we need to make sure that that's not happening either. I want to set the tone generator to, let's say, -1, which would be 9 dB over reference. So let's just try -1, see if the overload light comes on. It does not. Cool. All right, I'm going to just go ahead and drop that down to some number, and I'm going to set this to -0.5. All right, which is 9.5 dB over 0. Overload. Okay, so it's coming on before 0. And then I'm going to do it again at -0.5. So the next thing really is to do is to go ahead and check the VU calibration for 0 with a -10 input to all of the cards, all 8 of them, and then also check the overload indicator for anything 10 dB over reference. And by the way, 0 dB is 1 volt RMS, or is 2.828 volts peak to peak. If I put this on my scope, go at 0, the overload light's going to come on. My scope is just completely off the scale. Okay, I've got 2.82 volts peak to peak. That is 0 dB going into the deck at 1 kilohertz. And in case you're wondering what it looks like from the front with the meter calibrated, there's Channel 1's VU meter calibrated. Interestingly enough, however, that yesterday it was reading 0.315 or 0.316, depending. So let's just see where this volume control is, which you can barely make out. is at 7 on the dial. The service manual calls for 2 o'clock. Well, 7 is about 2 o'clock, but I'm going to use the 7 as a reference for all the channels. The overload indicator adjustment is up here on top of the board, and there is a pot up there that I can get to with an actual greenie tweaker. But I do want to point out something to you. Up here, by the way, this is gonna have to be shot in B-roll because it's too cumbersome to have to readjust this camera, so I'm gonna leave it down here for all the other settings, and I'll do the B-roll later. But up here, where this pot is, and the slot for the adjustment, there are 2 resistors that are really very close to that. Now, what you'll notice is that this one resistor, and it's the same for all the cards, the lead is painted white. Do not assume that that's insulated, because yes, the paint should have insulated. I have come to realize that that slot, which is electrically connected to the wiper of that pot, it will short against that lead of that resistor. So what I would like to do is to just go ahead and use a non-conductive tool, which I haven't really dug out yet, so you'll have to bear with me. Restarting the cameras. But I don't really have access to one right now. I could dig it out and it's going to take too long. What I'm going to do is I'm going to use a piece of heat shrink, and I'm going to insulate the shank of this greenie. And I'm only going to leave the very tip of this exposed so as to minimize the potential for shorting out the circuit.
Nip the tip. Who's first?
Now, we're just going to make a slight adjustment. Going back up to turn it off. Slowly going down until it illuminates. Let's just go ahead and drop the input level down. But I'm just going to go with -1 dB, no light, -0.5, nothing, -0.3. Okay, still no overload. So dropping it back down again, and I'm going to go to 0, 10 dB over reference. Still no light. So I need to drop it down just a little bit more. Oh shoot, all I had to do was touch it. All right, well, I'm on there now. Okay. 0. Good. And we'll just say -0.5 dB. Nothing. I want it to be repeatable. I want to make sure that it'll do it every time, 3 times in a row. Okay, cool. Let's see where it actually does come on. -1 dB, no overload. I'm going to do -1 again. Still nothing. -0.1. All right, so that is a good test. I like that. We'll go back to -10, give the meters a chance to relax. And let's just break this down, okay? I've got a -10 dB, 1 kilohertz signal going in to achieve 0 dB VU on the meter. The overload indicator is supposed to kick in at 10 more dB, which it's doing, okay? Meter's going to take the brunt of that, but the overload indicator is to basically keep the operator mindful of the fact that your transients are exceeding 10 dB over reference, and that's the whole purpose of it. One of the ways that this seems to be behaving is that the instant, it's the transient, it's the slew maybe of the tone becoming loud, because if I gradually raise it up all the way through there, it'll light by the time it gets to 0 dB, but it doesn't always light at, say, -0.2 or -0.1. The idea is to just get it to where it's on at 0 dB going in at 1 volt and doesn't come on below that level. And last but not least, channel 8. Right now I've got -10 at 1 kilohertz going in. I've got 0.317 RMS on the meter, 0.88 volts peak to peak. So we're at the same starting point. Let's go ahead and just go from -10 to say 0 dB. Okay, got an overload light. All right, but let's see exactly where it starts to come on. We'll start at -2. All right, nothing there. So -0.5. Oh, overload. Okay, so that is set too low. So let's try -0.7. All right, so we're in the ballpark. We're real close. But I've got it 0.5, so I'm gonna go ahead and set that to 0. Okay, so now let's see where that is actually coming on. So we'll start at -1. Nothing. We'll make sure that it repeats, -1. -0.5. At this point, I'd probably just call it done because I know it came on at 0 and it's not on at -0.5. -0.2. Just really wanted to see where the light actually comes on. Wow, it's not on. -0.2. Do -0.2 again. -0.1. Here we go. Watch this. Yeah. See there? Okay. We'll just see if it doesn't do it again. -0.1. Oh, didn't come on. So that means we're on the ragged edge of that. But at -0.1 dB, who gives a shit? Me, that's who. Okay, it comes on at 0. -0.1. All right, so it came on at -0.1. -0.1 again, didn't come on. And you know, I'm actually of the opinion, because what I do is I actually drop the level down to some lower number, okay? Not always the same number each time. And I think it has to do with actually how far it's coming up to get to, say, -0.1. And at that point, it will actually respond where it wouldn't have if it had actually come up a lesser distance, okay? And I'm speaking in physicalities here, but it's, you know, okay, so -7. This -7, I'm going to go to -0.1. Didn't come on. But I'm going to drop this down to -13 to -0.1. It's coming on at -0.1. Everything is pretty much dead on to within 1,000th of a volt as far as the audio is concerned. So I'm really pleased with that. The next step is that I'm expecting a delivery, and that is going to move us to a point where I can begin to actually comfortably run an expensive MRL alignment tape on this deck, and we'll all get to see that next. If you'll indulge me for just a minute, I'd like to give you a little bit of a tech tip. This is just one of the things that sticks in my craw. I am using RCA coaxial type cables. What I wanted to point out to you is if we take a look at the scope, you see how that baseline is just like really fuzzy? Okay, I'll even add some tone to it. It makes it really hard to set the peak-to-peak values because, well, do you go with the center of the curve or do you go to the top of the fuzziness? I am going to go ahead and use, well, video cable, but it's double shielded coaxial low impedance cable. And from that image right there, it's going to look this good. Right there. Okay, a nice pristine sine wave using low impedance cable instead of the high impedance coaxial cable that you can buy nowadays. And I still get the same exact voltage RMS that I'm supposed to be getting at -10 dB, 0.3 volts RMS. And that is incredibly sexy. The curves are in all the right places and no fuzziness to deal with. Let's go ahead and put the icing on the cake. Not the cherry, just the icing. I'm going to be looking for 0.46 volts RMS on the DMM and 1.3 volts peak to peak on the scope. Channel 1. That's going to be this adjustment right up here on top. This is what they call the monitor level, which is the playback head for all practical purposes.
MRL calibration tape, IEC equalization, at 355 nanowebers per meter, fringing compensated. 1 kilohertz. (10 kilohertz).
Now channel 2.
MRL calibration tape.
Track 3. Now I will point out to you that we know there's a problem with track 3 on the playback head. The DC resistance is half of what it's supposed to be, which is going to be much lower gain. I don't really expect to get full level out of this head.
1 kilohertz.
I actually got full level at 1 kilohertz, but we're going to see in a moment exactly how track 3 performs with the high frequencies. Track 4. Track 5.
MRL calibration tape.
Track 6. Track 7. Yeah, helps if you press the right button. Track 8. That one's already dead on. I am on track 8. I am in fact on track 8. And track 8 comes in at 0.46. Meters are registering roughly plus 4 dB. It's supposed to be about 3.6 or so, but still, that's in good shape. So now, we look at what they call the normal head, which is actually the record head, playing back the same information. And that adjustment is going to be, it's going to be the second pot down on each card. Let's see where we're at to start with.
MRL calibration tape, IEC equalization, at 355 nanowebers per meter, fringing compensated. 1 kilohertz.
Wow. These are hot. Track 2. Track 3, off the record head. Track 4. Wonder if I can get track 5 in the remaining amount of 1K tone. That's interesting. Well, that's not good. It's behaving as if the pot itself is loose. Very interesting. It's got some signs of having been soldered, not by me. Just gonna go ahead and tack solder some of that. Track 6. Track 7. Track 8. Okay, that's all 8, except for that one pot on card number 5, but it's better than it was. I'm going to go ahead now and use the 10K test on this tape to set the monitor playback EQ. And again, I want to get that to 0.46 volts RMS. The problem is going to be that my DMM won't register 10 kilohertz at that level, so I'm going to go strictly with the scope for all the high frequency stuff. But when we get to 50 hertz later, I'm going to go back to the DMM and the scope.
10 kilohertz.
Track 2. track 3. And this one is going to be, again, that one that is kind of problematic, okay, because I really don't know what to expect from this head. I mean, the DC resistance is half of what it's supposed to be. But let's see where we end up. That is actually maxed out and it's low. Okay, 1.14 divided by 1.414 divided by 2 is 0.4 volts. It's going to be close to maybe a dB and a half at most at 10 kilohertz. Probably going to be worse at 16K. But before we do that, let's go ahead and finish the rest of these. Track 4. Track 5.
10 kilohertz.
Track 6. Track 7. Track 8. Okay, moving on to 16 kilohertz.
16 kilohertz.
Okay. 1.3. Track 2. And track 3 at 16 kilohertz. All right, well, it's low, but you know, we could always just use it for like the bass guitar. Track 4, 16 kilohertz. Track 5 at 16 kilohertz. Track 6. Track 7 at 16. Track 8 at 16 kilohertz. Singing along, man. Okay, so now we'll move on to the 50 hertz test tone just to see what the overall performance is. Okay, shouldn't have to make any adjustments and it should come right in at, well, 1.3 volts peak to peak and 0.46 RMS. Now my DMM will register 16 kilohertz, but
50.
it's not going to read
Hertz.
the voltage. 50 hertz has got a little bit of a boost to it. Let's see what the other channels look like. Okay. There's really no adjustment for 50 hertz, so I just want to see what it looks like. Now that one. Now that is track 3, and interesting how it's way higher than the rest, which would make it really beneficial for bass guitar. Pretty cool. All right, one other thing. Now, we got these all adjusted and everything, but right now I want to go ahead and get ready to make the high frequency adjustments for the record head playback mode. And before I do that, I want to go ahead and just very quickly go through the levels of the record head gain again, just to make sure that they are where they need to be before I start the high frequency tweaks.
1 kilohertz.
0.46, 0.46, 0.46, 0.46, 0.4, come on, you know you want to. All right, well, we hit it once. 0.46, 0.46, 0.46. So, next thing we want to do is do the high frequency, starting with 10K. 10 kilohertz.
10 kilohertz.
That's what I said. Track 2. Track 3. Track 4. Track 5. Track 7. And track 8. Okay, now the 10 kilohertz has all been set to match the 1 kilohertz reference. However, because so much of the passive components in here are interactive, we already know that the 1 kilohertz reference has changed. So rather than actually go into the 16 kilohertz now, save wear and tear on the tape, I'm going to go ahead and re-rack this back to 1K and see where the levels are and make those adjustments before I move on to finalize the 16K response. Track 1, and this is overall gain. Yep, it's low, so we'll run that back up again. That's the one that's got the funky pot. All right, so the high frequency adjustment for 10K affected the overall gain, so I've got that back to where it's supposed to be, but of course then that is also going to change the high frequency gain as well, but not near as much as it had in the past. But I'm going to skip the 10K, go straight to 16K, and make the high frequency adjustments again, getting them dead on this time. Can't use the DMM on this because that meter does not respond to voltage at that frequency. So I'm going to exclusively use the scope for this, bringing all of the high frequency for each track to 1.3 volts peak to peak. I think it takes longer getting up and down and running around than it does to actually make the adjustment. I forgot what track I'm on. There we have it. I'm going to go ahead and run the 50 hertz test on this, and I'm just going to switch from channel to channel to channel to see where they are, because I'm not going to be changing any more gains. I just kind of want to see where it ends up. Okay, it's 0.55 RMS, 0.52, 0.55, 0.53, 0.53, 0.54, 0.55 again, 0.54. So we're in really good shape. I'm really happy with the way this thing's behaving. These frequencies are going to be pretty much dead on. With the frequency response, yes. Track 3, it's got that issue, but again, it's kind of a one-off thing, and it's going to serve its purpose despite the fact that it doesn't wake up in the morning in a good mood. So what I want to do now that we've got this fully calibrated for the playback, the playback is dead on, so now we can actually use the playhead kind of as a piece of test equipment in order to be able to set the record bias, the record EQ, and using the playback circuitry to confirm that those adjustments are correct. And in order to accomplish that, I've got this card on and an extender. And what I'm going to have to do is, hey, Jay? Yeah. You got a minute? It's going to be more like an hour. Just forego the coffee and just, what? Sorry to interrupt, but what I want to be able to do here is to feed all 8 channels the same tone from the same source, and I don't want to have to break out an audio DA. I'm gonna continue to sort of preamble this, and you get me hooked up.
I'll bring out my audio DA.
Okay, so we're going to do a DA anyway. On top of everything else, this deck was originally set up for 250 nanowebers per meter, and you can't even get that kind of tape anymore. So we're going to use 320 nanowebers per meter tape. Okay, so, and I'm not going to go through all that all the time, all right? I'm just going to call it 320. Okay, but I want to go ahead and set the bias up and confirm that the adjustments that I may or may not have to make are in fact correct.
I'll feed you tone. We'll give you, what, 1K, 10K, 16?
Yeah, just real quick, give me 1K.
1K.
All right, so we're right with there. You can go back to 10.
What's the frequency of the bias on this machine?
The frequency of the bias on this thing is kind of radical. It's 100K. So it's going to be, you know, it should not create harmonics even up to 20K. I have a hunch it might. Okay, it'll be readable like on the scope, but audibly, nah, not so much.
First time I've seen a unit since you've recapped it.
I'm pretty pleased with it. Learned a couple of things in the process, but I'm not going to spoil it for you. You have to watch the episode.
I'll probably be editing said episode as well.
Exactly. One interesting thing about this deck is that in the case of like a stereo deck, like if the Griffin episode, if you go back and look at the Griffin episode, I explained that they have a dummy load that is engaged when you're only recording one track at a time, because the oscillator, the erase and bias oscillators in there have to have a dummy load if you're only recording one track. They didn't do that here. What they did in this particular case is that they put a master oscillator in on the function board, and it creates the 100K that is going to be fed to each of these 8 cards. And each of these 8 cards has its own oscillator, but it's fed from the main oscillator. So there's actually a gain pot on each board for taking that master oscillator and kind of like re-amplifying it. The signal coming into each card from the master oscillator is only about a volt peak to peak. I can show that to you, but it's going to be fuzzy. And you know how we don't really like fuzzy. And there it is. I've got my scale set at 1 volt peak to peak, and it's there just a little over 1 volt peak to peak coming into the board. All right, now that's going into the pot. Coming out of that pot is going into the actual bias amplifier for each channel. So it's going into...
That won't be 1 volt then. That'll be...
It's going to be going into the bias level before it goes on to the record head. Is right here.
Oh, that's clean.
That's what he said.
Yeah.
And that's going into the pot. What's coming out of the pot is an attenuated signal that goes onto the record head, and that would be visible here. So that looks like about 20 volts peak to peak. Pretty close. I don't have the cursors exactly right, but that's 20.1. So that is actually what's going to the record head as bias right now. So
this card's good?
And it's pretty. That's a sexy curve. Let me tell you. I'm distracted.
That's what he said. So card 1 is good then. So move on.
Well, I mean, as far as the bias is concerned, now we could load up a tape, okay, and see exactly how that's behaving, because these values are important, but is it actually where these levels need to be in order to create a flat frequency response for that particular track?
Would it be a smart thing, since we're not the original owners of this machine, would it be in our best interest to just go down each card, because who knows what the last guy did with bias adjusting?
Yes.
Okay.
Yes. But I think before I sign off on this card, we should test it for record quality.
Okay.
All right, so we load up a tape. But you're absolutely right. I kind of want to do both things.
Yeah.
Because once I establish that bias is good and the frequency response is pretty much what I would expect from a Teac 80-8, we'll use these values, whatever these values turn out to be, we'll use these values to plug in for the other cards, and that way all we have to do is just tweak it a little bit in order to get those cards to perform to card 1. Card 1 is our reference.
Yeah. I only bring that up because tape's expensive. So wearing it back and forth and back and forth. I figure if we just get these...
This tape is going to have a lot of mileage on it.
Yeah.
Okay. But when we get everything set correctly, we're going to actually record, kind of make our own alignment tape.
Right.
Once we get this all set up, and we're going to record 5-10 minutes of whatever tape is left on that spool, and then cut it off and put it on the shelf. Right. Especially with head alignments, azimuth, zenith, and so forth, being able to get the deck back to factory spec and actually have a record, no pun intended, of what the deck was doing when it was brand new, and that's a nice place to be able to get back to.
Yeah.
So let's see where we're at with this. Okay.
Wow.
That's cool.
That's good.
All right, that just proves that it's working.
Right.
0.3 volts RMS and playback. Okay, so the record level is good.
Yeah.
Let's go to 18K.
18K.
Okay, got a bit of a boost there.
Yeah.
Okay, 16K.
16K.
Again, we got the boost. How about 20K?
20K. I mean, that's not the worst thing in the world.
We've got a little bit of high-end boost, but that's where the record EQ and peaking occurs. So let's go back to 18K. Record EQ. These are all set at about 12 o'clock, and they really don't do much. I get a little bit of a roll-off there. The record EQ is actually selecting between 15K and 20K. It's actually selecting a frequency, and it's behaving kind of like a very wide parametric equalizer.
Got it.
Because it is basically kind of picking a center frequency, and then the peak adjustment is actually adjusting the amplitude, supposedly. I went ahead and changed the record EQ and peaking, which has probably affected the 10K. What I want to do is just get to peak, all right, and I'm going to back the level down so I can use the VU meter as a guide, and then I'm going to increase the bias to 3 dB, okay? 1K? I'm just using the 1K tone to recalibrate my input, okay, which is supposed to be 0.3 of a volt RMS. Give me 10K.
10K.
That is like plus 0.5,
That's
where
what
I had plus 2 before.
That's within tolerances.
Okay. The erased head should be erasing the tape.
Yeah.
The bias is also going to kind of erase the tape as well. You got the erase head that's breathing fire onto the tape to get rid of whatever was on there, but then the record head has got bias on there, which is also going to help erase the tape. Let's real quick check 18K and move on. Okay.
18K rolling. Wow.
I'm a happy camper.
18K at a...
Try 20. Just see how bad it can get. See if there is a bad. I'm not
finding that to be a problem at all.
All right. I'm seeing a little bit of hovering going on there, and this is down. At worst, it was 1.5 dB down. Now it's only 1 dB down. And that's 20K.
That's at zero level, that's pretty significant. I mean, whenever you're mixing something, you're never going to have 20K at 0 dB in your mix anyway.
No, it's going to be just for harmonics.
Right. So that's beyond acceptable, especially for an 8-track machine. That's actually
of
rather
this
impressive.
vintage too.
Yeah.
All right. So I'm satisfied that card 1 is behaving.
Yep.
So let's move on to card 2. And that bouncing like that is the absence of a good erasure. Okay. Let me see 10K.
I don't like that at all. And 10K.
All right, well, that's in the ballpark.
Yeah.
But I'm not really...
What's the bias look like?
Oh, well, the bias is looking like... Oh, my God. That is horrendous.
What kind of a curve is that?
Well, it's a very mature curve because it's got wrinkles.
You can see some spots as well.
Yeah, there's liver spots. That is not good. So,
Cleaning that up is, how do you do that?
the fact that it's symmetrical, so to speak, is the transistors are doing what they're supposed to be doing. I gotta tell you, what that looks like to me, in all those years that I would be working on broadcast transmitters, that's like being overdriven, because it just, let's just get this tape off of here. I think I know what's going on. Let's take a look at the schematic. All right, and with the schematic, what we end up with is from the master oscillator, okay, the signal actually comes into each card, one of 8, but it comes in there from the master oscillator, and it comes in and hits that transistor right there, okay, and it provides a little bit of amplification. All right, there's a little bit of gain going on there, but because it's an emitter follower, the signal is actually going to be coming off of the emitter. It goes through this FET. Now, that FET transistor is basically controlled by the logic board. You apply the right voltage to that coming out of the logic chip that it's attached to, and it turns that on. It's just like a switch. Well, what I'm seeing here is that right here, all right, that resistor right there, that resistor is basically taking that signal to ground. And this wiper coming off of here is what's going to go into this circuit here. And this is interesting because the way this is configured, it's almost behaving kind of like a compressor. It's a limiter, all right? And so the signal that's coming in there, what happens is that coming off of that resistor right there and into this input for these transistors is it's going to cause this transformer right here to begin to take that oscillation, and it's isolating the signal coming in from where it's about to go. All right, but coming off of that wiper, and then after this transformer, all right, the signal comes out through that cap and look in there, heads right over to the erase head. Well, what's also interesting is that the same frequency and signal that's going to the erase head is also going to the record head through this pot. We haven't got that far yet because that's the bias adjustment. That's what's basically what we saw before, where I had 100 volts going into that pot, peak to peak, and only had 20 volts peak to peak coming off because we had reduced it just enough to be able to do the job of laying that signal onto the tape. I think we need to look right here. The other place that I'm monitoring this, where it looks really, really nasty, okay, is right here. I think that these transistors here are just amplifying what it's seeing. My scope is actually on the input to the bias level pot, which is going to the record head, and that's what it looks like coming off of those 2 transistors. But I think the input, we'll start with the inputs, and all right, I'm increasing it. It's overdriving that.
I've never seen a wave like that.
Look at there.
Oh, okay. So someone probably.
So this was turned up too high.
Okay. So the previous owner probably tried to compensate, didn't know what they were doing.
You know what? I'm not going to speculate because I've also been inside this deck and I may have bumped something. So I'm just going to say it's not where it was supposed to be, but we're getting there.
That looks symmetrical as hell.
It looks like a sine wave. Yeah. And what is it someone once said? Those are curves you can take home to mama. See, right there it begins to distort.
Yeah.
Right there it's symmetrical though.
Okay.
So that's pretty good.
I'm going to shift you over to 3.
Actually, I don't need audio because I'm just looking at biases.
That's true. You're right. I will just sit here in the corner and just admire the view.
Obviously, I didn't set him in the corner enough when he was a kid.
No, you did.
That looks as nasty as the last one.
Awesome. Oh, it just cleaned itself up all of a sudden.
That's not clean.
How much of adjustments are you making on the pot?
I mean, I'm just touching the facet of the greenie in order to just get it to that little bit. I mean, because ready? That's off. Okay, and I don't know if we can get a close-up of this, but that's off, all right? And it's on the ragged edge of the pot. I mean, I've probably turned it 10 degrees. Yeah. I don't want to overdrive it all that much.
I mean, if you want that cassette tape sound on an 80-8, I'd say go for it.
Oh, yeah, but we charge extra for that. Okay, so that's ballparked as far as I'm concerned.
Question.
Yes.
The voltage at J3 for the erase head, measured on an oscilloscope for a 65 dB erasure, is 110 volts peak to peak.
110?
110. So it says it in the service manual.
Oh, okay. Well, those are words on a page. I was looking for pictures.
Oh, right.
So it should be, so the spec calls for 110 volts peak to peak.
It is within spec if the ratio between the initially recorded 1K signal and the erased portion is more than 65 dB. Should erasure be insufficient, slowly rotate the trim pot marked erase and bias level, R111,
Yeah.
until a ratio of 65 dB is obtained.
Okay.
Voltage at J3 should be at 110 volts peak to peak. It took me reading this to find it because I don't look for pictures all the time.
So I had it set for 100 volts peak to peak because I could get away with that. Turns out I can't get away with it because I was still getting the other stuff. So I'm going to actually pause and go back to card 1, reset it to 110 volts peak. Actually, I'm satisfied with 120. I can get 120 out of it. I'm going to get better erasure.
Okay, as long as it doesn't mess any like coils up in the head or what have you.
The only issue is that at 120 volts peak to peak, 123 volts peak to peak begins distorting the sine wave.
Right.
So 110 gives you a little bit of latitude that you could probably live with.
Yeah. Well,
So I'm in a quandary because I know I can get 120 volts peak to peak out of it, but the book calls for 110 volts peak to peak. No pictures. So I say let's do it by the book.
What about 115? What if we split the difference? Because 5 dB is pretty significant.
He's just so big on negotiating. So we'll do 115 because that gets me away from potential distortion. The only thing that's going to really happen is, I mean, the erase head is it's going to get warm. I mean, we'll be lighting cigarettes on it. Hey, that's pretty cool. You got a Teac 80-8 with built-in cigarette lighter? Far out.
I mean, even the cars had those back in the day.
Yeah. Go to 115. See how touchy that is?
Yeah, it's incredibly touchy.
So that's 115. All right, so that's going to get me, per their specifications, better than 65 dB erasure.
Yeah. And the wave is still clean.
And it's still clean. I don't have a distortion analyzer to actually check the integrity of a sine wave.
So if anything, we've shown you how to set the eraser to 100 volts, 120, and 115.
If it gets to 130, sell. Take the greenie. All right. On that bottom pot, watch the scope.
Oh man, that is so sensitive. You can like watch my heart beat through my fingers.
She said,
Look at that. It's
yeah.
That's crazy sensitive.
See, for me, I would have put a different value pot in there.
Yeah.
That way you could get it more mid-range, and you'd have, a much smoother, more lackadaisical kind of an adjustment.
It's a little too high, a little too low, right there.
Okay. Goldilocks.
Yeah. That bias was just right. The Ampex bear said, "Oh, that's too much bias." The Scotch bear said, "Ooh, that's a little too low of bias." The Quantigy bear said that was just right.
I kind of picture Ampex being Mama Bear.
I think we adjusted 4 already to 115, but we'll double check. Woo! Yeah,
That is nastified.
that is crazy.
And the thing is, you wouldn't have needed that much if you were using 250 tape. Because, you know, the hotter the tape, the more it's going to take to erase the tape, but still.
My argument now is that since we're using 320 tape, that extra 5 volts might actually become a little bit useful.
It may be why we were getting ghost signals left on the tape, remaining on the tape. Wow, now that's actually,
That looks like about 120.
it's clean. I know that much.
So audience, look at how little he's moving the pot whenever he adjusts this. I mean,
I don't even know if you can tell how little it's adjusting.
Yeah.
But I mean, I don't want to raise that back up. Yep, it just fattens out.
Amazing.
Well, that is going to solve any audio distortion potentials that would have occurred. You know, because you've got to have a symmetrical sine wave on your bias. Otherwise, you're going to have all kinds of artifacts that are created in the audio. I feel real good about this.
As do I. I gotta go rescue something, so
Okay.
I'll keep you posted on what it is.
With a 10 kilohertz tone going in at minus 10 dB, I've got exactly 0 dB on the VU meter, but I want to check the bias, so I'm going to back the bias off just to see where my peak is. And the peak is +3. That's good. So from peak to 3 dB down, which is 0 dB VU. So that's exactly where that needs to be. We'll try a high frequency now. Now 18 kilohertz, just to see if we have to adjust the record EQ. And it's only down 1 dB. That's acceptable in this particular case. Now the record level, all right, that's good again. We'll check that against the 10K. Good to go. I'm going to re-rack the tape and move on. So let's do track 4. That's right where it's supposed to be. We haven't adjusted the bias yet, so let's get to that. 10 kilohertz. It's actually about +1 dB. So I'm going to back the bias off until it peaks. There's a peak right there, which is just a little over 3 dB on the VU meter. So increasing bias to drop 3 dB. Now, I want to check 1 kilohertz to set the record level, which is like less than half a dB down. So, not far to go. 18 kilohertz. Which is about a half a dB down, so it says. Well, this one actually has some sort of response. All right, 18 kilohertz at 0 dB VU. Track 5. Level is good. Let's see how well it records. Okay, so the level is high. I can just go ahead and adjust the record level now, but honestly, I just want to get it to that spot. 10 kilohertz. Whoa, hello. That's like +3 dB already. Where's peak on this? Wow, peak is... I'm going to adjust the record input level just to keep me on the meter scale. Wow. Okay. So I've adjusted the volume so that it reads +3 dB on the VU meter. I'm going to increase bias until it drops down to 0. That'll be 3 less dB at that point. Okay, so that's 3 less dB. Very close. Now, we'll see what that did to the record level. It's just a tad low, less than half a dB. I'm just going to tweak it now. 18 kilohertz, which is very high. So this is going to be a record EQ. Track 5 is really kind of hot at the higher frequency, 18 kilohertz. I want to check 10 kilohertz again, just to see if that bias can help me in this. Yeah. Check 1K again, see if that's affected my record level. Yeah, record level is right where it ought to be. So let's assume that I'm supposed to go to 18K. Get a little bit more high frequency out of this. It's less than a dB down, but it is down. Okay, moving on to channel 6. Okay, so it's a little bit high. I'm going to go ahead and just adjust the record level to 0 just to get started, and then we'll set the bias. 10 kilohertz. It's high, but we're just getting started. All right, I'm going to back this level down here because it's way off of scale. And increasing bias to -3. Now reset the record volume, 0. And we'll see where our level is at. Record level for 6 is good. Now we'll try high frequencies. Okay. And it is significantly high. It's like plus 2 dB hotter. Let's see where our record EQ and peaking are at. All right, let's see where 10K still is. Okay, so 10K is a little bit high. It's 2 dB high, so I want to check 1 kilohertz again. It's dead on. So, I might be able to just hit it with just a little more bias, just to sort of get that, because the 18 kilohertz was like much higher, it's like 2 dB high, and the 10 kilohertz adjusting the bias brought that into compliance, but I'm thinking I want to try to get it a little flatter. Right now I've got a boost at about, 11K, and I want 10K to be at 0, and I'd like 18K to be at 0 as well. So this is 18K. And it's like significantly high, but if I bring the bias up a little bit more, I can bring that 18K down to just a hair over 0. Now let's see what 10K looks like. Same as 18K. And I know 1K is still good because I haven't changed the record level, and there's really no EQ adjustments for 1 kilohertz. I could check 50 hertz, but I already know there's going to be a boost. Oh heck, let's check it out. Haven't changed anything as far as levels or EQ or anything for track 6, but let's just see what 50 hertz looks like. Yeah. Not surprised. Moving on to track 7. Okay, that level is low. And there's some significant dancing around. Well, got the right level going in, so I'm going to just adjust the record level to 0 for the time being. And let's see where the bias is. 10 kilohertz. Wow. Okay, I'm going to have to back this pot down. That bias was just almost totally maxed out. Okay, so that is peaked right there. Make sure I'm on 0. And then we'll just drop it down 3 dB. Okay, so we'll go back to calibrate the input. So that's calibrated. We'll just check the record level. All right, record level is off the charts. Okay, 1 kilohertz. We'll check 10 kilohertz. All right, that's reading 2 dB high. I want to check that against the 18 kilohertz. Yep, that's plus 3 dB. I'm going to cheat that with a little bit more bias. Okay, cool. And 1K. Very cool. 7 down, 1 to go. Track 8. All right, it's 1 dB low. I'm going to adjust the record level just to put it at 0 as a starting point. All right, and now we'll check bias. Okay, that level is low. So I'm going to back off on the, shoot, that thing just took off. Wow. Let me get this to peak. Shoot. All right, there's peak. There's 0 on the meter, increasing to 3 dB down. We'll go ahead and recalibrate at 1 kilohertz. So that's calibrated. That record level is off the charts. So I'm bringing this back down, and then we'll see if it in any way affected the 10 kilohertz after having adjusted that bias. Let's see where we end up there. Okay, it's about 1 dB high. So can probably cheat that with a little bit of bias, but let's check it at 18 kilohertz first. Not bad. Let's see if these record EQs help at all. You know, I almost wonder if these pots have never been adjusted. All right, that 18 kilohertz right now is registering a little bit above 0, the same amount above 0 as 10 kilohertz. So I'm going to go back to 10 and see if I can't bring that into compliance. Just barely touched it, that bias adjustment just added a little bit more to bring that 10 kilohertz down. Okay, and I'm going to go ahead and check the 18K now. Wow. You know, I could probably bring that 18K up just a little bit. See whether or not these record EQs. I cannot. Yeah. All right. Because these will not affect 10 kilohertz. Very cool. Now, one last check of 1 kilohertz. Dead on. Cool. Very cool. Now what I want to do is to just go ahead and test the erasure of the deck, because one of the specifications is that you record on it and then you roll the tape back and erase over it, record over it with no audio, and the signal left on the tape should be 65 dB down. I'd like it to be like all the way down. All right, the noise floor is probably approaching 65 dB anyway. So what they're suggesting is doable. Let's see if it actually achieves that. 1 kilohertz. Zero the counter so I know where to come back to. I have 0 VUs across the board. I'm going to start recording with the tape counter at all zeros. So I'm in record mode, and honestly, I could probably just listen right now to see if there was anything kind of bleeding through there, but I'm going to wait and then get to 10 on the tape counter and start my tone, like now. What I'm going to do is I'm going to record enough tone for me to be able to pull the connector off the back and go from channel to channel to channel with the volume on my speakers like loud. Okay, that way I can see if or hear what it might be left on the tape. I don't think there's going to be anything left on the tape, but I want to estimate exactly how long it'll take me to go from track to track to track. I'm figuring, 60 seconds. So I'm watching the stopwatch on the wall, and I'm just waiting for us to get to that point, and then I'm going to go back to silence for another 10, 15 seconds. That's a minute right there. The reason I leave silence at the end of that recording is that as I'm going from track to track to track, if I had stopped recording, then whatever I might have had on there from a previous test is going to be in there, and the speakers are going to be loud, and don't want that to wake anybody up. There's 30 seconds. Now I can actually monitor it now, and I got to tell you, I'm not hearing anything. I'm going to go from track to track to track just to see if there's anything there. At the end of all this, the goal wasn't to chase numbers on a page. It was to make the machine perform predictably every time. By setting E to E first, lining up playback on both heads, and then dialing in record level and bias, we're simply making sure the 80-8 behaves the same way every time you hit record. Bringing this deck from 185 to 320 nanowebers doesn't magically make it better, it puts it on a level to better perform. It's kind of like your car. It runs good when you use the recommended fuel, but you want better performance. tape is like gasoline. Higher octane requires adjusting the timing, the mixture. Well, you know all that. We've shown you how to get better performance from higher octane tape. From here on out, when something sounds a little bit off, we know it's the source material and not the machine lying to us. In other words, no knocking and no blown head gaskets. The real win.